students, so welcome back to my video lecture 3 on S block elements. So in video lecture 2 we were discussing about the physical properties of alkali metals and alkaline earth metals, wherein we discussed about atomic radius, ionic radius, okay, valency, ionization enthalpy and their physical appearance. Okay, I have also correlated between alkali metals and alkaline earth metals full. Okay, now in this video we will continue with the physical properties. We are left with metallic character, then okay, melting point and boiling point, density, and then we will be talking about the color. After that we will speak about okay, the chemical properties of alkali metals and alkaline earth metals simultaneously. Okay, yes students, now we will be talking about the next okay, this is fifth physical property, isn't it? Fifth or sixth? Okay, we discussed atomic radius, ionic radius, okay, valency, ionization enthalpy, physical appearance. So this is the sixth physical property of alkali metals and alkaline earth metals. What is it? Metallic character. Metallic character. Okay, we know metallic character, okay, is inversely proportional to ionization energy, isn't it? Metallic character is inversely proportional to what? It is inversely proportional to ionization enthalpy, isn't it? It is inversely proportional to ionization enthalpy. By the way, what do you mean by a metal, guys? Okay, what is a metal? Okay, metal is any element which has the metal is any element which has the tendency to lose the electrons. Okay, any element which has the tendency to lose the electrons. Any element which has the tendency to lose the electron is said to be a metal. Okay, more the tendency to lose the electron, more will be the metallic character. Okay, more the tendency to lose the electrons, more will be the character. Now, which character? Metallic character. Okay, so I am telling you that metallic character is inversely proportional to ionization enthalpy. Okay, yes, more the ionization enthalpy, okay, more the ionization enthalpy, that means it will be very difficult to lose the electron. Okay, more higher the ionization enthalpy, that means you have to supply more energy to remove the electron. If you are supplying more energy to remove the electron from a element, say from this element, okay, so I have to supply more and more energy to remove an outermost electron. That means this metal, this element has very less tendency to lose its electron. If it has less tendency to lose its electron, it will have less metallic character. Is that correct? Okay, if this metal, if this element is requiring very high energy to lose its electron, that means it has no tendency to lose the electron. Okay, isn't it? If it has no tendency to lose the electron, it will have less metallic character. That is the idea. Okay, so metallic character is inversely proportional to ionization enthalpy. Now, lesser the ionization enthalpy, that means okay, if you supply very less energy, it is sufficient so that the metal will lose the electron. The metal will lose its outermost electron. Even if you give very less energy, it will lose its electron. That means this metal has more tendency to lose its electron. Okay, that is why it is now requiring only less energy to lose its electron. Okay, so that means this metal has more metallic character. It has more tendency to lose its electron. More the tendency to lose the electrons, more will be the metallic character. Okay, if the tendency to lose the electron is more, ionization enthalpy will be less. Okay, if the tendency to lose the electron is less, then ionization enthalpy will be more. That is what I am telling you. Metallic character is inversely proportional to what? Ionization enthalpy, isn't it? Okay, now what happens to ionization enthalpy along the period and down the group? Yeah, okay, we have learned this already. Along the period, okay, we know ionization enthalpy along the period increases, correct? Increases along the period, whereas down the group Okay, ionization enthalpy decreases. Say yes or no. Okay, ionization enthalpy decreases down the group. Now let us talk about the metallic character of alkali metals and alkaline earth metals. Okay, so for alkali metals we have lithium, sodium, okay, potassium, rubidium and cesium. In alkaline earth metals we have beryllium, magnesium, calcium, strontium, barium. Okay, we know as we go down the group, okay, ionization enthalpy decreases. As we go down the alkaline earth metal group, ionization enthalpy decreases down the group. Okay, as the ionization enthalpy decreases, metallic character increases. The tendency to lose the electron increases. Metallic character increases. So what is the order of metallic character among alkali metals, and what is the order of, okay, metallic character among alkaline earth metals? Look at it. The order of metallic character among, okay, alkali metals and among alkaline earth metals. Okay, so down the group, ionization enthalpy decreases, that means metallic character increases. So lithium has less metallic character than sodium, then potassium, then rubidium, then cesium. Okay, cesium has highest metallic character. What about, okay, among alkaline earth metals? The same trend follows. Beryllium is less metallic when compared to what? Magnesium, then calcium, then strontium, then barium. Okay, now if we compare, okay, the metallic character of alkali and alkaline earth metals, okay, along the period ionization enthalpy increases. Okay, when the ionization enthalpy increases, the tendency to lose the electron decreases. That means metallic character decreases, isn't it? Okay, so I can conclude here, alkali metals, okay, are more metallic, okay, than alkaline earth metals. Okay, is that clear? So that's all about the metallic character. Okay, no big deal here. Fine. Now, okay, next. Let us move on to the next one. Okay, which is the next physical property. Okay, so the next physical property is very important. That is melting point and boiling point. Yeah, melting point and boiling point. Yes. Okay. So very important. Okay, this is, I'm talking about melting and boiling point. Okay, yes. So look here, the melting and boiling point, okay, depends upon two factors. One is, it depends upon, okay, melting point and boiling point depends upon two factors. One is, okay, number of valence electrons, correct? Okay, number of valence electrons, it is directly proportional here in this case, directly proportional, and also it also depends upon the size. It also depends upon what? Size. Okay, for size it is inversely proportional. Okay, inversely proportional. Are you getting my point? Okay, so melting point and boiling point depends upon two factors. Which are those two factors? Number of valence electrons, directly proportional, and size, inversely proportional. This means to say melting point and boiling point are directly proportional to number of valence electrons. Melting point and boiling point depends upon what? They are inversely proportional to size. Are you getting my point? So when the number of valence electrons, we also know that we have learnt this in chemical bonding, okay, that melting point and boiling point depends upon, okay, the strength of the bond, correct? Strength of the bond. Okay, strength of the bond, correct? Okay, now stronger the bond, stronger the bond, then you have to, okay, supply more heat to melt a given compound. Okay, if the bond is weak, then you have to supply less energy to break the bond, to melt the compound, isn't it? Okay, that is what it means. Melting point and boiling point is directly proportional to the strength of the bond. Correct? Okay, look here, as the number of valence electrons increases, okay, as the number of valence electrons increases, metallic bonds increases. Okay, in alkali metals and alkaline earth metals, as the number of valence electrons increases, okay, metallic bond increases. As the metallic bond increases, the strength, okay, as the strength increases, obviously melting point and boiling point will increase. Please note this point. Okay, and as the size increases, melting point and boiling point decreases. As the size increases, melting point and boiling point decreases. Okay, look here, I am going to consider, okay, yes, alkali metals, that is lithium, sodium, potassium, rubidium, cesium, okay, and alkaline earth metals, beryllium, magnesium, calcium, strontium and barium. Correct? Okay, strontium and barium. We know the general outer electronic configuration of alkali metals is inert gas core, okay, yes, NS1, whereas for alkaline earth metals, inert gas core, okay, NS2, isn't it? NS2. Any doubts with this? Well, by this configuration, I am very much clear that alkali metals have 1 valence electrons, whereas alkaline earth metals have, okay, 2 valence electrons. That means alkaline earth metals can form, these can form 2 metallic bonds, okay, yes, whereas alkali metals can form 1 metallic bond. They can form 1 metallic bond. Okay, they can form 1 metallic bond. Okay, as the number of bonds increases, the strength increases, the melting point and boiling point increases. Correct? Okay, and also melting point and boiling point depends upon size. Melting point and boiling point depends upon size. We know, okay, lesser the size, more is the melting point. Okay, now more the size, lesser will be the melting point and boiling point. We know as we go from alkali metals to alkaline earth metals, as we go from alkali metals to alkaline earth metals, size decreases. Size decreases. As the size decreases, melting point and boiling point will increase. As we go down the group, okay, the size increases. Okay, please again note this point. Okay, is it confusing? Hope it is not confusing. Okay, see, I was telling you that don't get confused. Very simple logic. Okay, I hope you know this. Melting point and boiling point depends upon 2 factors. One is number of valence electrons. Okay, more the number of valence electrons, more is the melting point and boiling point, because they are directly proportional. Okay, melting point and boiling point also depends upon what size. More the size, lesser will be the melting point and boiling point, because they are inversely proportional. Okay, correct? See, alkali metals, they have only 1 valence electrons. That means they can form 1 metallic bond. Okay, yes, okay, whereas alkaline earth metals have 2 valence electrons. That means they can form 2 metallic bonds. More the number of bonds, more will be the strength. More the strength, more is the melting point and boiling point. Hence, by this I can conclude that alkaline earth metals have more melting point and boiling point than alkali metals. Very simple. Next, and also, okay, the size of alkali metals is less than the size of, the size of alkaline earth metals is less than the size of alkali metals, because as we go, okay, along the period, the size decreases, isn't it? Okay, lesser the size, more is the melting point and boiling point. So based on the 2 factors, based on the combined factors of this as well as this, okay, I can clearly say that alkaline earth metals have more melting point and boiling point than alkali metals. Okay, why alkaline earth metals have more melting point and boiling point than alkali metals? Because they have 2 valence electrons, they can form 2 metallic bonds. Okay, as the bond strength increases, the melting point and boiling point increases. And also, okay, alkaline earth metals are smaller than alkali metals. Alkaline earth metals are smaller than alkali metals. Smaller the size, more will be the melting point and boiling point. So my conclusion is alkaline earth metals have more melting point and boiling point than alkali metals. Okay, yes, so I'm going to conclude it here. Yes, yes, alkaline earth metals have more melting point and boiling point than okay, what, alkali metals. So because of the two reasons which I quoted earlier. Okay, what is the order of melting point and boiling point down the group? Okay, we know as we go down the group, the size increases. As the size increases, melting point and boiling point decreases. So what is the order among alkali metals? Among alkali metals, the order of melting point and boiling point is lithium has more boiling point than than sodium, than potassium, than rubidium, than cesium. Okay, this is the order of melting point among alkali metals. And what is the order of melting point among alkaline earth metals? Beryllium more than magnesium, more than calcium, more than strontium, more than barium. Okay, is that simple? So that is all about the melting point and the boiling point. Okay, melting point and the boiling point. Now guys, quite important, next one, density. Okay, density of alkali metals and density of alkaline earth metals. Okay, density of alkali metals and density of alkaline earth metals. Okay, yes. Next, this is the 8th physical property, isn't it? Okay, yes. 6th, or is it the 7th one? Okay, 7th physical property. We are talking about what? Density of alkali metals and alkaline earth metals. Again, name the different alkali metals. We have lithium, sodium, potassium, rubidium, cesium. Okay, alkaline earth metals: beryllium, magnesium, calcium, strontium, and barium. Okay, that's correct. We know density is equal to mass by volume, correct? Okay, as the mass increases, density increases. As the volume increases, density decreases, correct? Okay, density is directly proportional to mass. Okay, so according to this equation, I can say that okay, density is directly proportional to mass, whereas density is inversely proportional to volume. Okay, as mass increases, density increases. Okay, as mass decreases, density decreases. As volume increases, density decreases. They are inversely proportional. Okay, now what about the density of alkali metals and alkaline earth metals? Okay, let me consider sodium and magnesium. Okay, sodium is an alkali metal, magnesium is an alkaline earth metal. Okay, correct? Okay, what is the atomic mass of sodium? 23. I'm talking about atomic mass. Okay, atomic mass. Atomic mass of sodium is 23, whereas the atomic mass of magnesium is 24. Okay, atomic mass of sodium is 23 and atomic mass of magnesium is 24. That means alkaline earth metals have more atomic mass than alkali metals. Okay, as the mass increases, obviously density increases. Is that simple? Okay, now once again I repeat, okay, alkaline earth metals have more atomic mass than alkali metals. Okay, as the mass increases, density increases. Therefore the conclusion is alkaline earth metals have more density than alkali metals, isn't it? Okay, so can I conclude here? Yeah, the conclusion is alkaline earth metals, okay, yes, are denser than alkali metals, are denser than what? Alkali metals. Alkaline earth metals are denser than alkali metals. Okay, hope you got the reason. Now what happens to the density, okay, down the group? What happens to the density down the group, okay, in alkali metals and alkaline earth metals? Look here, okay, if I consider the density If I consider the density down the group, okay. Again, let us apply the same logic. Density is equal to mass by volume, okay. Yes. Here, okay, down the group, if I consider down the group, okay, of course, okay, down the group, of course, mass increases. Okay, mass increases because the atomic mass keeps on increasing, isn't it? What is the atomic mass of lithium? 7. What is the atomic mass of sodium? Okay, atomic mass of lithium is 7. Atomic mass of sodium is 23. Atomic mass of potassium is somewhere around 39. So atomic mass is increasing. Atomic mass is increasing. Okay, we know as the mass increases, obviously density should increase. Okay, density should increase, isn't it? Okay, correct. But also down the group, okay, down the group, we know down the group size increases, atomic size increases. As the size increases, volume will increase, correct. Down the group size increases, atomic size increases, that means volume will also increase. As the volume increases, density should decrease, isn't it? Density should decrease. See here, both is happening. Density is increasing because of increase in mass down the group. Okay, density is decreasing because of increase in volume down the group. Then what is going to happen to the density? Will it cancel? Okay, will it remain the same throughout along the period? No, look here, the increase in mass will be more than increase in volume. Note this point. Note this point. Down the group, okay, increase in mass, okay, will be more than, okay, okay, yes, the increase in volume will be more than the increase in volume. Increase in mass is more than the increase in volume. Okay, since the mass increases more than volume, the density will increase down the group. The density will increase down the group. Got it? Clear? Okay, so here both the things are happening. Even the mass is increasing, volume is also increasing. As the mass increases, density increases, but as the volume increases, density should decrease. But the increase in mass is more than the increase in volume. As a result, density will increase down the group. Correct? Density will increase down the group. So what should happen to the density from lithium to cesium? It should increase. What should happen to the density from beryllium to barium? It should increase. Correct? But there are exceptions here. There are exceptions. What are those exceptions? Let us understand those exceptions. Okay. Exception. So my conclusion is, okay, density, okay, increases, okay, increases down the group. The density increases down the group, okay, due to enormous increase in atomic mass. Okay, note down it. But there is an exception to this. There is an exception to this. Look at here. Observe, okay, alkali metals. So from lithium to sodium, density should increase. From sodium to potassium, it should increase. From potassium to rubidium, it should increase. Rubidium to cesium, it should increase, isn't it? But look at the variation. No doubt, lithium, okay, has less density than potassium. Potassium has less density than sodium. Okay, density, next thing remains the same. Then rubidium, then cesium. Okay, than cesium. Okay, there is an exception. Okay, so according to us, potassium should have more density than sodium, but potassium has less density than sodium. This is an exception here. Potassium has less density than sodium. Okay, next, how about in alkaline earth metals? So beryllium to magnesium, density should increase. Magnesium to calcium, it should increase. Calcium to strontium, it should increase. Strontium to barium, it should increase. But here also there is exception. What is it? Okay, density increases from magnesium to calcium, calcium to beryllium, and then from, okay, what? Strontium, and then barium. Got it? Okay, look here. Beryllium comes at the middle. Okay, that means it has very high density when compared to magnesium and calcium. Okay, but less density than the remaining two elements. Okay, this is an exception. Please please remind and remember these two exceptions when you are talking about the density of alkali metals and alkaline earth metals. Okay, this is the exception. Got it? Yes. Now the last physical property, guys. The last physical property. Okay, what is that last physical property? Yeah, okay, yes. We will be speaking about the color of the flame. The color of the flame. Yes, okay. Eighth physical property. Color of the flame. Okay, yes. Color of the flame. Well, students, we know that alkali metals and alkaline earth metals, I don't know how many times I should write the same words throughout the chapter. Okay, alkali metals and alkaline earth metals have low ionization enthalpy, isn't it? Okay, they have low ionization enthalpy. Obviously, alkali metals ionization enthalpy is least, okay, when compared to alkaline, but still both of them have low ionization enthalpy. That means if you supply even very less energy, okay, even if you supply minimum energy for alkali metals and alkaline earth metals, it will become easy for us to remove the electron, isn't it? We know this very well. Okay, see what is going to happen if we supply even if very small amount of energy to alkali metals and alkaline earth metals. The outermost electron in the alkali metals and alkaline earth metals will absorb this energy and gets excited to the higher energy state. Okay, even if you supply minimum energy, okay, very minimum energy, the outermost electron, since it has low ionization enthalpy, it will absorb that energy and gets excited to the higher energy state. But in the higher energy state, it is unstable. Therefore, it returns back to the ground state, and when it returns back to the ground state, it starts emitting radiations. It will start emitting radiations. That is why when alkali metals and alkaline earth metals are kept in flame, okay, even in candle flame, okay, look here, when alkali metals and alkaline earth metals are kept in flame, when they are introduced to flame, they impart color to the flame. They will impart color to the flame. Are you getting my point? Okay, yes. So they have low ionization enthalpy. Even the energy of this flame, kind of Bunsen flame or candle, okay, anything is fine. This energy is sufficient enough for this electron to get excited, but in the higher energy state it is unstable. Therefore, it returns back to the ground state and emits radiations. Different radiations are emitted. Okay, yes. So that is why, okay, when the different radiations are emitted, the flame will acquire color. The flame will acquire what? Color. So let us see what are the different colors, okay, imparted to the flame by different elements now. Okay, what are the different colors emitted by different elements, okay, to the flame now? Okay, so if you consider alkali metals, we have lithium, okay, sodium, potassium, rubidium and cesium. Look here, lithium, okay, will emit, okay, yes, crimson red color, okay, yes. Sodium will emit, okay, golden yellow color. It will impart golden yellow color to the flame. Potassium will, okay, emit violet color. It will impart violet color to the flame. Rubidium will give red violet. It will impart red violet to the flame. And then cesium will impart blue color to the flame. Blue color to the flame. This is with respect to what? Alkali metals. Now, if you consider alkaline earth metals like beryllium, magnesium, calcium, strontium and barium. These two, they do not impart any color because their ionization enthalpy is very high. Okay, they have high ionization enthalpy. Okay, the energy of the flame is not sufficient to, okay, ionize the last electron, therefore they do not impart any color. We'll say they impart white color, white. Whereas calcium, it imparts brick red color to the flame, brick red color. Strontium will impart crimson red, okay, and barium will give apple green color to the flame, apple green color to the flame. Okay, got it? So guys, this is all about the different physical properties of alkali metals and alkaline earth metals. So in the next videos we will be talking about the chemical properties. Okay, thank you.